Hey guys, welcome to our video on solving problems involving pH. Today we're going to be covering some common types of problems and the solutions that you'll come across in exams, and then go over some more abstract examples. As with all things in chemistry, it's important for you to think systematically. So if you look at our pH equation, we have two unknown variables, the pH itself and the concentration of H+. Thus, they'll give you one of the variables, so they might give you the concentration of H+, and then ask you to find the pH. Same for the other way around, they might give the pH and ask you to find the concentration of H+. It's important for you to also know the concept of POH, which we'll go over in this video. Sometimes they'll give you the concentration of hydroxide, not H+, hydroxide, and then ask you to find pH. Thus, the second equation is incredibly important. So before we get stuck into some problems, it's important for us to establish the relationship between pH and POH. So hopefully you remember this relationship here, which says that the concentration of H+ times OH- equals 10 to the power of minus 14 moles. So that's for a solution of free water. Like with all things, for me especially, it's very easy to memorize formulas if I understand where they come from. So this explanation requires you to have some form of understanding of logs. So if we take the negative log of both sides, we get negative log 10 to the power of minus 14 equals negative log the concentration of H+ times OH-. Now if we go over our log rules, that gives you this here. So 14 equals negative log H3O+ minus log OH-. You might recognize this here as nothing but the pH equation, which is pH equals negative log H3O+. Therefore, the POH equals negative log OH-. Hence we have this very important function here. In this way, if you get the pH, you can work out the POH, and if you have the POH, you can work out the pH, as shown below. It's also very important for you to understand this as well, so make a note of this, in that the POH is negative log the concentration of hydroxide. So over here we have our first problem. I want you to keep close attention to the working out, as this is quite important, especially in an exam scenario. You may be presented with a problem that you're not quite sure of. In these cases, it's important to have as good a go as possible while still maintaining good working out, as it shows some kind of understanding and you may be rewarded some marks. It's not a guarantee though. So this is our first problem. What is the pH for a 0.05 molar solution of hydrochloric acid? So the first thing I want you to do is write down your dissociation equation. Many people get tricked, especially for diprotic acids, into thinking that the concentration of the acid, so in this case 0.05 molar, is the same as the concentration of H+ in solution. Whilst in this case it's true, because as I've said here, HCl and H+ are in a 1-to-1 molar ratio. For many polyprotic acids, this is not the case. However, in this case, the concentration of H+ in solution is 0.05 molar. Next, we write our equation. This is a very important step, and you could lose marks if you don't write your equation. Then we show substitution. So pH equals negative log of 0.05. Next, put it into your calculator and round to the correct significant figures, in this case 2. Now we have problem 2. So what is the concentration of H+ in a solution with pH 5.2? First step, as always, write down your equation. Unlike problem 1, where we were given the concentration of H+ indirectly and told to find pH, In this problem, it's the other way around. So we're told to find the concentration of H+, but we're only given the pH. Now I'll show you a nice trick of how to get from the pH equation, which is here, to a relationship that allows you to easily find the concentration of H+, but it requires you to know your log rules. For those of you that don't have or haven't covered your log rules yet, just know that for logs, we can take the base and make it this the power. And we get this relationship here, which is incredibly important. So 10 to the power of negative of the pH equals the concentration of H+. If you want to memorize that, if you want to understand it, it's fine by me. Just make sure you know it. So if the concentration of, if the pH, is 5.2, we just put that into our new equation that we've learned here, and we get this result here. So 10 to the power of minus 5.2 equals the concentration of H+. Put that into your calculator, round to the correct number of significant figures, and you get this value here. In problem 3, we're asked to find the pH of a solution of sodium hydroxide with concentration 0.02 moles. The first thing as always, regardless of if you know what to do or not, is to write down your dissociation equation. In this case, sodium hydroxide reversibly dissociates into sodium and a hydroxide anion. Therefore, as sodium hydroxide and the hydroxide anion are in a 1-to-1 molar ratio, if there is 0.02 moles of sodium hydroxide, there are also 0.02 moles of the hydroxide anion. I'll bring your attention to the right hand side now. As I previously stated, this relationship here is very important for when you want to work out the pH, but you're given the concentration of hydroxide as we have found here. As always, the first thing we do is write down our equation, then we substitute. In this case, I've rearranged first, but you can substitute and then rearrange, whatever you prefer. Personally, I prefer to rearrange and then substitute after. So if you do some basic math, you move the OH under and you get the concentration of H3O plus equals 10 to the power of minus 14 divided by the concentration of OH minus, because these two are being multiplied together in the original equation. So if you bring it over to the other side, it becomes a division. We have this value, we have the concentration of hydroxide, which we know is 0.02. Hence, the concentration of H3O plus equals 10 to the power of minus 14 divided by 0.02. Now that we have this, we can work out the pH, as is required in the original question. Again, the first thing we do is write down our equation. pH equals negative log the concentration of H plus or H3O plus, and I reiterate, they're interchangeable. They mean the same thing. I've been a little lazy here, but what you can do is find an answer for this, write it down or store it into your calculator, and then substitute it here. Or you can write this whole thing in bulk into your calculator. Just make sure you have log 10. Put that into your calculator and you should get the pH equals 12.3 with the correct number of significant figures. In our next problem, we're asked to find the pH of a solution, given that the pOH of the solution is 2.13. We know that the equation for pOH is negative log OH minus. You could do this the long way and try and find the concentration of H plus and work backwards, but using and remembering this relationship is incredibly important and will save you a lot of time in exams. So we know that 14 equals pH plus POH. However, we know that POH is 2.13. Hence, 14 is pH plus 2.13. Now we rearrange, so plus moves to the other side, becomes a negative. So the pH is 14 minus 2.13, and you should get an answer of 11.19 when rounded to the correct number of significant figures. Problem 5 tests your understanding of the pH scale. Here we asked how many more hydrogen ions are there in a solution with pH 4 compared to that of one with pH 6. As we know, there is a relationship we can draw between the concentration of hydrogen ions and the pH. We extrapolated this relationship in a previous question. This is incredibly important for you to understand. Thus, going off of this, between pH intervals, there is a tenfold difference in the concentration of H+. Therefore, between pHs 4 and 6, there are 2 intervals, and thus there would be 10 squared difference. You can also work this out in your calculator by manually putting 10 to the power of negative 4 minus 10 to the power of negative 6, which is the 2 pHs that are requested in the question. Or you can just remember the fact that for each interval in pH, there's a tenfold difference. Either way, you will get to the same answer of 10 squared. Don't fall into the trap of thinking pH 6 would have more hydrogen ions than a solution with pH 4. As we know, the lower the pH, the more acidic a substance is due to the fact that it has more H+ ions. You can also reason this out in the fact that the pH is a negative logarithmic scale. Thus, a solution with pH 4 is 100 times greater in its H+ concentration than one with pH 6. Now that you've mastered a selection of the common problems you get in regards to pH, I have a more abstract and definitely a harder example. So if you're up for it, what is the pH of a solution containing the following 3 chemicals? 0.3 moles of hydrochloric acid, 0.6 moles of sodium hydroxide, and 0.1 moles of nitric acid. If you stick to what you know, it actually isn't too hard to solve, but we'll go through it right now. As always, the first thing I want you to do is write down your dissociation equations, which I've done here. So HCl dissolves to form H+ and chloride, nitric acid, H+ and NO3-, sodium hydroxide to form a sodium ion and a hydroxide anion. To make things simple, everything is a 1-to-1 molar ratio. So there is 0.3 moles of H+ from the HCl, there is 0.1 moles of H+ from the HNO3, and there is 0.6 moles of hydroxide from the NaOH. If you put your thinking caps on, if we put all of these solutions into a beaker, the H+ and the OH- will react to form water and neutralize. So if we add the total amount of H+, so 0.3 and 0.1, we have a total of 0.4 moles of H+ in solution. However, there is 0.6 moles of hydroxide. Hence, 0.4 moles of this hydroxide will react and neutralize with the 0.4 moles of this H+, shown in this manner. Thus, there is a net amount of 0.2 moles of hydroxide, because remember, we had 0.6 moles here. If 0.4 moles reacts with the H+, we have 0.2 left. Hence, that 0.2 is left in solution, surrounded by water and all these random ions, such as a sodium, a nitrate, and a chloride, which doesn't really affect the pH. Hence, the real moneymaker is this 0.2 moles of hydroxide that are left. That is what we will use to calculate the pH. This is a very important take-home for harder questions. They'll likely involve multiple solutions. Just remember the fact that H plus and OH minus in solution self-react and make water, which has a neutral pH and does not contribute to the pH at all. So you need to find the net amount of ions that are left. In this case, it's 0.2 moles of hydroxide. Now to take the concentration of hydroxide and turn it into pH, we'll do this in a manner we've already learned. So the first thing is write your relationship or equation, rearrange, and then substitute. Once again, I've put this entire thing into my calculator at the very end, but you could also just find an answer and write it down here and memorize it. Or yeah, just have it there. Now that we have our concentration of H+, we can work out the pH. So pH is negative log H+. Now you put all of this into your equation as you know the concentration of H+, and you get a pH of 13. And this makes sense. So if we have 0.2 moles of hydroxide left over in a solution with all these acids, it isn't surprising that we would get a very basic pH, because the rest of these acids have been neutralized and form water. This concludes our module on acid and base pH problems. It's incredibly important that you keep practicing and master these concepts. It is also important that you understand the types of questions you're going to get and memorize and understand the formulas that you can apply to each question.